Hello everyone, welcome to my channel. I am Krishnan Dupine. In this video, we are going to solve the first 10 problems of the QMB paper of ISI MSQMS 2016. In the earlier videos, I have solved the QMA part, so please check out that. Let's begin. Question number 1 is, we have to evaluate expression given here. I equal to 0 to infinity, summation j equal to 0 to infinity, summation k equal to 0 to infinity, 1 by 3 to the power I, 3 to the power j into 3 to the power k, where I not equal to j not equal to k. So here you can see these terms are independent terms. So you can write this as this: I equal to 0 to infinity 1 by 3 to the power I into summation k j equal to 0 to infinity 1 by 3 to the power j into summation k equal to 0 to infinity 1 by 3 to the power k. So these three terms all are same, so I can write once and I can make it to the power 3. So for this is an infinite GP series where the first term is 1 and the common ratio is 1 by 3. So this will be 1 by 2 by 3 whole cube. So it will be 3 by 2 whole power 3, which is 27 by 8. So this is the answer. 1b. A restaurant offers 5 choices of appetizer, 10 choices of main meal and 4 choices of dessert. A customer can choose to eat just one course or 2 different courses or all 3 courses. Assuming all choices are available, how many different possible meals does the restaurant offer? Here we have to think that the customer can choose one appetizer or one main meal or one dessert, or he or she can choose both of them or this one and this one, or the customer can choose all the 3 elements. So there are 3 combinations here. First of all, the first one is the customer is choosing only one item. That means only one appetizer, only one main meal or only one dessert. So from 5 appetizer, one choice, plus because these are all distinct, from 10 main meals, one, and from 4 choices of dessert, one. Now suppose the customer is choosing 2 different courses, like one appetizer and one main meal, or one main meal and one dessert, or one appetizer and one dessert. So how can it be done? So 5c1 into 10c1 plus 10c1 into 4c1 plus 4c1 into 5c1. Now the last case is the customer is choosing one appetizer and one main meal and one dessert. So how many ways this can be done? 5c1 into 10c1 into 4c1. Okay, just do this sum and you will get 329. This is the answer. Question number 2a. A function g is given which has derivated g dash x for all x satisfying g dash 0 equal to 2 and given g of x plus y equal to e to the power y gx plus e to the power x gy for all xy belongs to R. R is a set of real numbers. Now we have to show that g dash x plus gx minus 2 e to the power x equal to 0. From this we can write limit h tending to 0 g of 0 plus h minus g0 divided by h equal to 2. Now before that, from this expression we can, if you put x equal to y equal to 0, then we will get g of 0 equal to e to the power 0, which is 1 into g0 plus e to the power 0, 1 into g0. So g0 equal to 2g0. That means g0 is equal to 0. We can put the g0 value here. Then we will get gh by h equal to 2. G dash x equal to limit h tending to 0 g of x plus h minus gx divided by h. If we express g of x plus h by the formula given here, then we will get e to the power h gx plus e to the power x gh minus gx divided by h. Take the gx common, then we will get e to the power h minus 1, and keep this e to the power x here into gh here, whole divided by h. Gx into limit h tending to 0 e to the power h minus 1 divided by h, which is equal to 1, plus e to the power x into limit h tending to 0 gh by h, which we have written here 2. So from here we have got g dash x minus gx minus 2 e to the power x equal to 0. So this is the answer. Here the given expression is little bit wrong. This will be a minus sign here. So the correct answer is g dash x minus gx minus 2 to the power x equal to 0. 2b. A matrix A is given here. We have to show that the determinant of A is independent of theta. So we are writing determinant of A. If we just perform this operation, r1 dash equal to r1 minus r2 and r2 dash equal to r2 minus r3, then we will get, after performing this operation, we will get this part. Now if we take common 2 sine alpha minus beta by 2 from the first row and 2 sine beta minus gamma by 2 from the second row, then we will get, on the outside we will get 4 sine alpha minus beta by 2 into sine beta minus gamma by 2 into inside the determinant we get this. Now if we expand this determinant with respect to this third column, then we will get 4 sine alpha minus beta by 2 sine beta minus gamma by 2 into, this will be sine 2 theta plus beta plus gamma by 2 into cos 2 theta plus alpha plus beta by 2 minus sine 2 theta plus alpha plus beta by 2 into cos 2 theta plus beta plus gamma by 2, which is sine 2 theta plus beta plus gamma by 2 minus 2 theta plus alpha plus beta by 2, which is 4 sine alpha minus beta by 2 sine beta minus gamma by 2, and this is sine gamma minus alpha by 2. So this is the final expression and it is independent of theta, which we had to prove. So it is done. Question number 3a, we have to find an integration I equal to triple integral x to the power L minus 1, y to the power m minus 1, z to the power n minus 1, 1 minus x minus y minus z whole power p minus 1 dx dy dz, where L, M, N, P, these all are greater than equal to 1, taken over the tetrahedron bounded by the planes x equal to 0, y equal to 0, z equal to 0 and x plus y plus z equal to 1. Now take these assumptions first. Let x plus y plus z is equal to u, x plus y equal to uv and x equal to uvw. Then we have y equal to uv minus x, x is uvw, so it is uv into 1 minus w, and z is equal to u minus x plus y is uv, so it is u into 1 minus v, and after this transformation the limit will be uvw, these all limits will go from 0 to 1. Now for this transformation we have to calculate the Jacobian. The Jacobian J is del of uvw divided by del xyz. If you calculate this Jacobian, you will get minus u square v. I am assuming that you know how to calculate Jacobian. Now after this the integral would be triple integral mod of j is u square v into the given expression, which is the first term is x to the power L minus 1, which is uvw to the power L minus 1. After that it is y to the power m minus 1, which is uv 1 minus w whole power m minus 1. After that it is z to the power n minus 1, which is u into 1 minus v whole power n minus 1. And after that it is 1 minus x minus y minus z whole power p minus 1, which is 1 minus u to the power p minus 1 du dv dw. Now all these values of u v w varies from 0 to 1, so I am writing this w equal to 0 to 1, v equal to 0 to 1 and u equal to 0 to 1. Now you can see that you can independently write u v w, so I am writing the limits of u first, then v, then w. So it is u equal to 0 to 1. If you take the all u's one side, you will get u to the power L plus m plus n minus 1 into 1 minus u whole power p minus 1 du. As these are independent, so we can write into v equal to 0 to 1. Similarly, if you take all the v one side, you will get v to the power L plus m minus 1 into 1 minus v whole power n minus 1 dv. Similarly for w, we will get w equal to 0 to 1, w to the power L minus 1 into 1 minus w whole power m minus 1 dw. So we can see this is the beta function, where from this we can write this is beta L plus m plus n comma p into, for this will be beta L plus m comma n, and for this will be beta L m. If we expand all these beta functions, we will get gamma L plus m plus n into gamma p divided by gamma L plus m plus n plus p. Similarly here it will be gamma L plus m into gamma n divided by gamma L plus m plus n. Similarly here it will be gamma L into gamma m divided by gamma L plus m. Now you can cancel out gamma L plus m here, gamma L plus n and it is here. You will get gamma L into gamma m into gamma n into gamma p divided by gamma L plus m plus n plus p. So these we had to prove, and this is done. Question number 3b. Consider the following two experiments. In the first experiment, a fair coin is tossed 6 times. So as this is a fair coin, so probability of head and probability of tail, this is always half. This coin is tossed 6 times. So P is the probability of getting exactly 4 heads in a row in this experiment. So there are total 6 places. We have to choose 4 heads in a row. So this can be this place, these can be 4 heads, and these 2 can be 2 tails. We can choose these 4 heads, the other 2 then will be tail, and we can choose the last 4. These will be heads and these 2 will be tail. So we can see that there are total 3 cases where this exactly 4 heads in a row can occur. So then this probability P will be equal to, as there are 3 cases, so it is 3 into, there will be 4 heads, so it is half to the power 4 into, also the other 2 cases probability of tail is half, so this will be 3 divided by 2 to the power 6, which is 64. Now the second experiment is a pair of fair coins are simultaneously tossed 3 times, and Q is the probability of getting a pair of heads exactly twice in a row in the second experiment. For any time, as these 2 pair of fair coins are simultaneously tossed, so the sample space S is 2 head, head tail, tail head or tail tail. The probability Q is getting a pair of heads exactly twice in a row. So either first time it can be a headed, and second time it will be a headed, and third time this will be anything among these 3. And the second case will be the first can be any of these 3 and the other 2 are simultaneously headed and headed. So there are 2 cases here. So how this is done? This is Q divided by, among these 4 cases, how many ways HH can be done? 1 into second time 1 into this place any of 3, so 3C1. And for this case, this will be 3C1 into how many ways this? 1 into 1 divided by total number of cases is, the sample space contains 4 points, and this is, the experiment is done 3 times by tossing these coins 3 times. So this is 4 cube. So this is 6 divided by 64. The correct option is Q is greater than P. 4a. Rectangle is inscribed in the acute angle triangle ABC with one side of the rectangle along the base BC and one vertex in AB, another vertex in AC. Find the dimension of the rectangle having the maximum area. So if you draw this, suppose this is x-axis and this is y. Now this triangle, this is suppose the base, which is BC, and this triangle, suppose this is C. Now this is 0 0, and suppose this point is A0 and this point is suppose BH. Then this is the height, this is H. Now this rectangle which is inscribed in this triangle, this is H. Now give that a name EFGH. Suppose the coordinates of E is xy and the coordinates of F is x dash y dash. Then H is x0 and G is x dash 0. Now the area of this triangle ABC is half into length of BC. BC length is A into the H is the height is H. So it is AH by 2. Now if we see the equation of this line of this side AB, we will get this is x minus 0 divided by b minus 0 equal to y minus 0 divided by h minus 0. As xy, that E point is any point and F point is any point on this side, so we can write this way, and this is y equal to hx divided by b. Similarly, if we calculate the equation of AC, similarly we will get it is x dash a minus a divided by b minus a equal to y dash minus 0 by h minus 0, which is equal to y dash equal to h into x dash minus a divided by b minus a. Now as this is a triangle, so this length of EH is equal to FG, so we get y equal to y dash. So then we will get hx divided by b equal to h of x dash s minus a b minus a. Then we are getting a relation between x dash and x, which is x dash equal to b minus a by b plus a. Now the area of this rectangle EFGH, which is equal to the length of EF or GH is x dash minus x, and this length EH or FG is equal to y. So the area is x dash a minus x into y. Now x dash is b minus a divided by bx plus a minus x into y. Y value we have got before hx by b, so this will be ah divided by b x minus x square by b. Now perform the derivative with respect to x. We will get, suppose this area is a, then we will get dA dx, which is equal to h by b 1 minus 2x by b. If we make it x equal to 0, then we will get x equal to b by 2, and if we again perform the derivative, we will get it is minus 2ah by b square, which is less than 0. So at x equal to b by 2, the area is maximum. We have to find the dimension of this rectangle. So the sides EF equal to GH, this is x dash minus x. Now that equal to b minus a by b into, this is b by 2 plus a minus b by 2, which is equal to a by 2, and the other side y equal to hx divided by b, which is h by b into x is b by 2, which is h by 2. So the dimension of this rectangle is the side which is along the base of this triangle, this side EF or GH, it is half of BC, because this is A and this is A by 2, half of BC, and the other side EH or FG, this is the half of the height of the triangle. So here the height is h, and the area of this rectangle is half of the area of this triangle ABC. So this is the answer. 4b. For all real number xy, you have to show that first is the triangle inequality. Mod of x plus y is less equal to mod x plus mod y for all xy which is a real number. So according to the property of absolute value, we know that this is true, that minus mod of x is less than equal to x less than equal to mod x, and similarly for y this is true. Now we are going to use this theorem which says that mod of b less equal to a if and only if minus a less equal to b less equal to a. We are going to use this property here. Y is less than equal to mod y. If we just add mod x both the sides, then we'll get mod x plus y less than equal to mod x plus mod y, and again for this x is less than equal to mod x. If we just add y both sides, then we will get x plus y is less than equal to mod x plus y. Now from these two we can write x plus y is less equal to mod x plus mod y. This is number 1. Again for this minus mod y less than equal to y. Now if we add minus mod x both sides, then we will get minus mod x minus mod y is less equal to minus mod x plus y, and again minus mod x is less than equal to x. Then again if we add y both sides, then we get minus mod x plus y less than equal to this will be x plus y. So from these two we are getting minus of mod x plus mod y is less than equal to x plus y. This is 2. So from 1 and 2 we are getting that minus mod x plus mod y is less than equal to x plus y less than equal to mod x plus mod y. So from this, and according to the theorem which I told you before, we are getting that mod of x plus y is less than equal to mod x plus mod y. This is proved. Now for the second part, we have to prove mod of x minus y is greater than equal to mod x minus mod y. According to this, we are taking two parts. One is x minus y, other one is y. So we can write x minus y plus y is less than equal to mod of x minus y plus mod of y. Now this is mod x less equal to mod of x minus y plus y, which is mod of x minus y is greater than equal to mod x minus mod y. So this is also proof. 5a. Fx is given bracket x minus x, where this function bracket x is the least integer greater than or equal to x. Suppose suppose a is an integer, and suppose x belongs to this interval a minus 1 to a, where a minus 1 is an integer and a is an integer, then this bracket x will be equal to a, because a is the least integer which is greater than x. Now we have to show that fx is continuous at all non-integral values of x. At first we will show that fx is discontinuous at all integral values of x. How we will show? Suppose for this a is a integer. Limit x tending to a minus fx. If we calculate this, then for this a belongs to this interval, so this will be equal to limit x tending to a minus, this fx will be equal to a minus x, which is a minus a equal to g. Now limit x tending to a plus fx. For this x belongs to this interval a to a plus 1, then this is equal to bracket x then equal to a plus 1 minus x, and this will be a plus 1 minus a, which is 1. So this left hand limit is not equal to this right hand limit, so fx is discontinuous at all integer points. For the non-integral points, suppose p is a non-integral point, so it belongs to R minus Z. Then, and suppose P belongs to this interval a minus 1 to a. If we calculate limit extending to P plus fx, then this is obviously a minus x and it will be a minus p. And similarly, if we calculate this one, limit extend to p minus fx, this will also be the same, which is equal to a minus x, and this will be a minus p. So these two are same, and also fx value at p, so fp is also equal to a minus p. So these three values are same, so we can say that for all non-integral points p, f is continuous. Question number 5b, if one root of the equation x square plus ax plus b equal to 0 is also root of x square plus mx plus n equal to 0, then you have to show this other root is a root of this equation. So the first x square plus ax plus b equal to 0, say R1 and R2 are the two roots of this equation. Then R1 plus R2 equal to minus a and R1 R2 equal to b. Now this is, suppose R1 is a root of the equation x square plus mx plus n equal to 0. Then it will satisfy this equation x plus m R1 plus n equal to 0. Now from this we can see here that R1 equal to minus a minus R2, so just put here minus a minus R2 whole square plus m into minus a minus R2 plus n equal to 0. Then it will be a square plus 2a R2 plus R2 square minus am minus m R2 plus n equal to 0, which will be equal to R2 square plus 2a minus m R2 plus a square minus am plus n equal to 0. So R2 is a root of this equation. So I have completed the first 5 problems of this QMB part. In the next video it will be the next 5 problems. First stay tuned for that and see you in the next one. Till then, goodbye. Thank you.